So we're going to go through a few examples of finding limits algebraically. Here's the first example. It says find the limit as x approaches 3 of the function x plus 4 over x minus 5. I know a little bit about this function already. It's a rational function, and it has a discontinuity at 5. It makes the denominator 0, and actually I think I can even figure out what's happening there. What do you think, Ms. Stewart?
It's probably an asymptote.
Yeah, there is. I think there is an asymptote at x equals 5. I don't have to really worry about that because that's no place even remotely close to where I'm trying to find the limit. I'm just trying to find the limit as x approaches 3. And as you recall, I can just plug in 3 for x because I know that the function is continuous around this point. So I'll stick in a 3 on top. I got 3 plus 4 over 3 minus 5. So that gives me 7 over negative 2. I like to write it as negative 7 halves. Is that the limit?
I think it is. You're done.
Here we have another function. I want to find the limit as x approaches 2 of this function here. And remember, when we're finding the limit, you're always looking to see what the function is doing. In other words, what the y value is doing. I could plug in 2, but there are all those squares and everything else. I like simplifying my functions first, which means factoring and seeing if you can divide anything out. So let's go ahead and factor. Let's see, x and x, factors of negative 2, 2 and 1. It looks like I want an x minus 2 and an x plus 1. And in the denominator, factors of x, factors of negative 6. Well, I'm thinking probably a 3 and a 2 will work. X minus 2, x plus 3. Did I factor that correctly?
Beautiful.
I think so. Hey, look what I see. Boom, I can divide those out. Remember our removable discontinuities? Well, there it is. So, in order to find the limit as x approaches 2, it's much easier now. I can just substitute that 2 in for my x. And voila, 3/5. It's that easy. That's my y value as my x is getting infinitely close to 2. And let's just get an idea of what this would look like. We know how to graph those. There's going to be a vertical asymptote. You don't have to do this, but I like to do it. I know I have a horizontal asymptote at 1. Let's see, so it's going to look something like this, something like that. At 2, I know there's a removable discontinuity, so there's a hole there. But if that hole were filled in, the y value would be 3/5. In other words, if I'm honing in from the right and honing in from the left, the y value would be 3/5. And I found that algebraically.
So what is the limit as x approaches 4 of 2 over x minus 4? Well, I already know what's going to happen when I put in a 4 for x. I'm going to have a 0 on the bottom, so it's undefined at 4. And there's nothing that I can factor on top. I mean, there's no way to make the top a 0. So in fact, I know what type of discontinuity it is. Do you know, Ms. Stewart?
It's asymptotic.
Yes, there happens to be an asymptote. It's an infinite discontinuity at 4. So I already know that the limit does not exist. There's an asymptote here. I'm either going up to infinity or down to negative infinity or one of each or something like that. So I'm actually going to look closer to see what's happening as I approach 4 from both sides, both the positive and negative side. I want to see what's happening exactly to this function as I approach 4 from the positive side. I already know there's an asymptote here, so I already know that the limit does not exist, and I'm going to write that down. What do you think, Ms. Stewart? Does not exist.
The limit does not exist.
Yeah, very nice. Yeah, very good. Okay, so I know I'm approaching infinity or negative infinity. I want to see exactly which one I'm approaching. So I'm going to pick some value on the positive side of 4, and I'll pick something slightly bigger than 4. It could be anything, but I'm just going to pick 4.1. So I have 4.1 minus 4. That gives me 0.1. So I have 2 over 0.1. 2 over 0.1, I think that's 20.
It is.
That's a fairly big number. But what would happen if I picked something even closer to 4? Because really, that's what I'm talking about. Like if I picked 4.001 and I subtracted 4 from it, I would get 2 over 0.001 That is, let's see, this would be 20, 200, 2,000. So what do you suppose is happening as I get closer and closer to 4, but on the positive side? Like if I picked 4.000000001
You're getting kooky
minus
now.
4, I would get some enormous positive values. So you can in fact see that the closer I get to 4, the bigger this fraction is going to be, the bigger this value is going to be, and in fact I am approaching positive infinity. So the limit does not exist, and I'm approaching positive infinity.
So Mr. Haas walked us through the limit as x approached 4 from the positive side. Let's look if we're coming in on x value of 4 from the negative side, a little bit to the left of 4. I already know the limit is not going to exist. The limit does not exist, sorry, because I have an asymptote, right? So my y values are either shooting up that asymptote or shooting down towards negative infinity or positive infinity. So let's figure out what's happening when I'm coming in from the left. So what is a little to the left of 4? Well, I don't know. You can, again, pick a number that's handy, maybe 3.9. That seems pretty close to 4. That's going to give me negative 0.1. When I divide those, I get negative 20. So my y value is already shooting down. Let's try something a little closer to 4, maybe 3.999. Again, you can choose any numbers you like. Let's see, 0.001. When I divide that, I'm going to get negative 2,000. Woo! That y value is shooting on down towards negative infinity. So my limit does not exist, and the reason it does not exist is because of the asymptote, and my y values are going down to negative infinity. So this would be considered your answer. Find the limit, my limit does not exist, and this is why. So let's just look again at the 3 types of limits that you're going to encounter when we're approaching a constant. The limit as x approaches 5 in this case. In this case, we can just plug in 5. And see what the y equals. It's continuous around 5, right? There's no asymptote or anything happening, so I can just substitute in 5 for my x and find my limit, which is 0 divided by 7, which equals 0. So as x approaches 5, my y is approaching 0. That's my limit.
So 0 in the numerator, that's just 0.
Oh yeah.
Oh yeah, 0 in the denominator, that's something, that's a whole other issue. Okay.
Let's look at 0
I always get that mixed up.
denominator. I know. Let's look at 0 in the denominator. Now I'm finding the limit as x approaches 5. Now I do have a problem. I have a discontinuity there, but look. It's a removable discontinuity, so I can still find the limit by substituting in my 5. So that's 2 over 6, which is the same as 1/3. So that would be my limit. As x approaches 5, my y is approaching 1/3. I'm honing in on a y value of 1/3. Okay? The third scenario is when, ooh, I've got an asymptote. There's nothing I can remove. That asymptote exists. I know right away the limit does not exist. And then you could explore y. You could plug in values a little to the left of 5, if you're asked about that, and see what's happening to your y. You can plug in values a little to the right of 5 to see your reasons, but you know the limit does not exist.